Hi, everyone. Oh, not using this. Thanks for everyone for coming today. So I thought I'd basically focus this talk on one project that our group has been working on over the past, I guess, 6 months to 1 year. And we have some initial results, and I thought what better place to kind of talk about it than this conference. So the title of this project and talk is Learning to Reconstruct CT Scans from Few Planar X-rays. And our team we have a few people collaborating on this project. Ashok is here, Lawrence, who I saw Lawrence there, who's going to talk, I think, right after me. Tucker, me, of course, and then the person doing most of the work, which is our student, Yuran, also a Rice student. So I'm sure I don't have to say what CT scans are since in this audience, but I would like to mention that CT scanners, right, they make 3D volume representations of anatomy, and they require usually several hundreds of views of X-ray measurements. Okay, and these CT scans, because of their rich 3D information, right, they're the standard of care for all sorts of medical applications, some of which include radiation planning, disease and injury diagnosis, and imaging fractures. And so they're very useful tools, as I'm sure everyone here is quite aware of. But one issue, right, is that CTs are not very easy to get a hold of in many parts of the world. And even in countries with CT scanners, there's quite a big disparity in where they're actually located, right? It's not like every single clinic has a bunch of CT scanners. They're expensive, maintenance is an issue, energy grid problems, and so on. And so there's this problem that accessibility to CTs is not there in a lot of places. And so in those cases, what do? Well, they rely typically on X-rays for a lot of applications instead of CT. And so in comparison to CTs, there's been studies out there showing that the number of X-ray scanners in the world, in different parts of the world, far outnumber the number of CT scanners, okay? And so this is kind of the motivation of our work, which is there's this sparsity of CT, but we have a lot of X-ray. And so one question that naturally came up is, okay, if we have access to X-ray machines, what can we actually reasonably reconstruct from very few X-rays of a given piece of anatomy? That is, put in another way, can we actually synthesize a CT scan, right, from very sparse X-ray views? Now, obviously, we can't possibly get every single detail of a CT scan. I pose it in this way, but the question maybe more generally is how much of 3D can we actually infer from maybe 1 or 2 X-ray views? Okay, and so this reconstruction model here, I keep it vague in this slide, but it's some kind of model that we're going to hopefully be able to do this inference. The challenge, of course, is that this is a very ill-posed problem, right? From just 2 views, how do you get 3D information? And so our solution has been mentioned in a bunch of the other talks is there's some priors that we need, right, to do this effectively because the data itself, which are the X-rays, aren't enough. Okay, and so we're going to take a pretty classical approach, which is to use a data set, a training data set, and use learning, machine learning to do this. Okay, and so in line with several of the other talks today, right, let's use deep generative models to do this, and the question is, how good can they be? Okay, and deep generative models, as has been touched on, right, so we train a deep generative model, and as has been touched on, these deep generative models, right, my group in particular is quite interested in these generative models, not just for medical imaging, but also for a lot of natural imaging problems. And this has been shown, we can do all sorts of things with deep generative models, like creating images, in-painting, which means filling in missing values, fixing data corruptions, right, which is quite relevant to medical imaging, and then the type of problem that we're interested in, which is sparse reconstruction problems. Okay. So the setup we take is that we assume we have some training data, right, at hand. And this training data is going to consist of it's called paired data, where we have X-rays along with the CT volume that those X-rays correspond to. Now, I know some of you might be thinking this might be a rather difficult assumption to make in practice, and that's true. For now, we're making a simplified assumption that we have CTs and X-rays. One way to think about this, at least experimentally for now, is that we can take a CT scan and synthetically create X-rays from it. Of course, in the clinic, there's an issue of being able to actually take a CT scan and X-ray at the same time, but that's something we'll get to. But so for now, we assume this paired data where we have n patients, let's say, and t views of the same volume. And we're going to train this deep model that's going to take X-ray views as input and output, it's going to learn how to output these synthesized volumes. And in particular, the way it's trained, right, is a pretty standard objective for these reconstruction deep generative models, which is we have this ground truth volume, and we assign some loss to it to make sure that reconstructions, right, are close to what the ground truth is, right? And obviously, the more we train the model, we expect the model to get closer and closer to the ground truth pairs. And here, we just use a very simple objective known as an L1 error. And if I go a little bit more into detail for those who are interested, the main question is, how do we design this model? And I think here is something interesting we're trying, which is leveraging some other work outside of medical imaging. It's an area in computer vision called view synthesis, where you have multiple views of a 3D scene, and you're trying to infer about the 3D scene itself. So we're taking that to this problem. So our inputs, again, are T views, T X-ray views. We pass them through some network. For those who know, this is a UNet architecture. And the basic idea is this UNet outputs some features, okay, some 2D features for each. And now let's think about this 3D space that we're trying to infer, which is the CT volume. And for every point in that CT volume, these are 3D points, we project them onto the features, and then essentially just train another network that learns to map the coordinate of that 3D point along with those features to predict the output voxels. Okay, so quite simply, it's just we take features from the image and then infer for every 3D location using another neural network how to combine those features with that coordinate to make a prediction of the output. And we can do that for every single output pixel to synthesize a CT volume. Okay, and the idea here is that we're leveraging the fact that we know these 2D images are projections of the 3D space, and that's how we get those features. For those interested, there's this work called Pixel Nerf that we based this idea on, called neural radiance fields from one or few images, and so we're basically designing this algorithm using those ideas in mind. Okay, so we have some preliminary results that we can share using just a public lung image data set, the LIDC IDRI data set. And so here we take these CT volumes. They don't have X-rays, so we generate them with the DRR generator. And we do standard training testing where we divide the data set, and then we train on one and test on the other. And just for those interested, the X-rays are of size 128 squared, so we're not dealing with big images for now. And the CT volumes are 128 cubed. And here's just some results that we have so far. It's visual inspection is always hard, but just to give you an idea, right? If we have an input X-ray, we show the ground truth slices up top and the synthesized CT slices on the bottom. Obviously, we can't get every single small detail, but you'll notice that the general shapes of the images are quite there. And so this is quite promising for us. And remember, this is just from one single view of the CT volume. And a couple of things that we found, right? So this is with one view. If you look at different patients who have different anatomy, obviously, the method is clearly capable of modeling the different anatomy correctly. So it's not just outputting the same kind of mean anatomy for every single person. So that's one good thing. We also see that when we have two views, right, the reconstruction improves as we would expect. So this is just for one patient. Up top is the ground truth. The second row is what happens when our model sees one view of the patient. The third row shows what happens when the model gets two views. And in terms of accuracy, up top we see with PSNR, which is admittedly not the greatest metric, but it does give us some sense roughly that the fact that we're improving from 23 dB to 27. And this kind of comes in line to one clear question, which is how do we evaluate such an algorithm, right? PSNR is not the greatest metric for actual anatomical or clinical use. And so this is something we're working on now, right? We have this initial prototype, and we're trying to work with our colleagues into better evaluation. So in particular, well, I'll get to that next. The first thing is we want to first have a sense of where we're wrong. As John mentioned earlier, one key thing is, if you remember in his work, is also knowing where the reconstructions are uncertain. So that's something we're actively trying to do as well, a probabilistic approach. And the second one is what I was referring to is one way to evaluate that we're talking about is to actually say, once we reconstruct the scans, if we were to do radiation planning from the scan that was reconstructed versus the true scan, how close would those plans actually intersect? So that's one way of thinking about, is this reconstruction actually useful for certain application? And in particular, we're working with some cervix data from the MD Anderson. Another question, which is natural, is okay, how does X-ray quality, right, impact the performance? And how do we think about trading off X-ray quality with the cost of each of the different X-ray types? And how does that impact our performance? And finally, this is kind of a key problem with a lot of these deep generative models, is they often work well for cases which are very typical. And when you have the abnormal cases, let's say, or cases that are very rare, we don't know how these will actually work, right? And that's maybe the cases that matter the most. And so that's also part of our evaluation that we want to explore next. And actually, that's it. So I left a couple of minutes for questions. Yeah.
Can you hear me?
Yeah.
Very interesting presentation. I'm a pulmonologist, so I deal a lot with the X-rays, and I think the value of this especially is that, do I get a CT scan or not? So if I get this X-ray and I can look at this and decide what I saw in the X-ray and what you generate just gives me adequate information, I can save many, many CT scans, because we do lots of chest CTs. As you said, there are so many CT scans in the US that can cover the whole world. So why we do a lot, and we expose the patients to radiation, and that's cumulatively important. So I think the application would be, can I avoid doing more CT scans by just looking at this conversion? Yeah,
the radiation angle is also another issue, right? To avoid that also would be...
It's a huge issue. Yeah. We get so many CT scans.
Thank you.
Thank you. One last question.
Thank you for the talk. Other than more views of the X-rays, what else could we incorporate into such a model? I'm thinking something like ultrasound or other patient data. Other what data? Or other patient data that can go along and recreate something more. You mean for CTs? Like what other data could be incorporated besides X-rays to reconstruct CTs? Is that what you mean? Right. We're probably not going to have more X-rays, but can we make the model stronger? Well, we can definitely make the model stronger. What you're asking is interesting, is can we incorporate other data? That's actually not something I've thought about as much. There's definitely ways to make the model stronger. For example, allowing for various uncertainty in the angle of the X-ray, because right now we assume we know the angle perfectly. These are things we kind of simplified for now in our proof of concept stage. So those can improve. But actually, to be honest, I haven't thought about what other data could be used to do the reconstruction. If you have any suggestions, let me know.
Let's thank Guha again. Then we have the last speaker.